All right, so now we're going to talk about what are called shooting methods for the solution of boundary value problems. Okay, so, so boundary value problems. It's called the shooting method. And the basic idea behind the shooting method is to convert the problem of solving a boundary value problem into two parts, one of which involves the solution of a corresponding initial value problem, and the second of which involves some sort of root finding. Okay, so let's see what I mean by that. So let's say we have a second order 2-point boundary value problem. Okay, x double prime is equal to f of t, x and x prime, with boundary data x of a is equal to alpha and x of b is equal to beta. Okay, so what I'm going to do is so this is a boundary value problem. And what I'm going to do is I'm going to convert it to an initial value problem. X double prime is equal to f of t, x and x prime. And then, of course, in practice, what you oftentimes will do is that you will convert that second order differential equation into a system of two first order equations. Okay, and then you have x of a is equal to alpha, and then you're going to guess at some initial velocity. Okay, x prime of a is equal to z, where z is sort of some unknown, if you will. Okay, and the basic idea then is that you want to solve the sort of root finding problem. Okay, so you have a solution x. I'm going to think of it as being parametrically dependent on z. Okay, so I'm going to have x at a point b, but parametrically dependent on z. Okay, and I want to have that this is equal to beta. All right, so I'm going to try to solve for z so that the solution of the initial value problem, where z is the initial velocity, at time b, right, is equal to b beta, which is the right boundary condition that's like on the original initial value problem. So I'm going to try to solve for z such that the solution of the initial value problem, right, with this initial condition x prime of a is equal to z, right, satisfies the right endpoint boundary condition. Okay, so that's the basic idea, right? You take a boundary value problem, you relax this right endpoint condition. This gives you an initial value problem with an unknown initial velocity, which you guess at. Okay, so so once you've guessed that initial velocity, it's like you will get a solution of this initial value problem, which you can evaluate at time b. If it is the right value, which is beta, then you're done. If not, then you try to iterate to change z so that you get the right boundary condition. So that's sort of the basic idea behind the shooting method. Okay. So let's see where we go from this. All right, so I define phi of z to be x sub z. So I'm going to think of x as parametrically dependent on z. Okay, xz beta minus xcb minus beta. And you want to solve phi of z equals to 0 for z. And you can do this using some iterative methods. So iterative root finding method. Okay. So one way to do this, of course, is with the secant method. So the secant method, if you recall, is a little bit like the Newton method, except that in place of the the gradient of the function, it's like which is in the Newton method, you replace that by a secant approximation of the gradient, right? So you look at the line through the secant, so z0 phi of z0 and z1 phi of z1. So you have to have two initial guesses for z, all right? So you have some sort of function. You have a point z0 and z1, right? So maybe this is what the function looks like. Right, this is phi of z. This is z1. This is z0. All right, then this is the secant line, and want to see where it intersects with the x-axis. All right, so you know that your equation looks like y is equal to phi z1 minus phi z0 divided by z1 minus z0 times z minus z1 plus phi z1. You want to find z such that y equals to 0. Okay, so that gives me that 0 is equal to phi z1 minus phi z2 divided by z1 minus z2, 0, z minus z1 plus phi z1. This tells me that z is equal to z1 minus phi z1, z1 minus z0 over phi z1 minus phi z0. Okay, so this is really like the Newton update. That's like where this is the residual error, and then this is the approximation of the inverse, well, the approximation of the reciprocal of the derivative, right? Okay, so it's an iterative method. So this is what I'm going to call Z2. Okay, so the idea is that based on Z0 and Z1, I can get Z2, and then based on Z1 and Z2, I can get Z3, and I can keep iterating this. So I iterate until sort of phi Cn is small enough. Okay. So that's the basic idea. And then once that's small enough, you stop the process. So another way to sort of think about this is that if you have, what this is basically telling you is that if you have some sort of initial value problem solver, like a one-step method, and you have some sort of root finding method, you can combine the two of them to give you something which is going to give you the solution of a boundary value problem. Okay, so that's, if you will, it's like the basic idea behind the shooting method. Okay, so let me just stop here for now, and then I'll say something a little bit about what you can do if the differential equation is a linear differential equation. But for now, let's just stop here.